the essence of what you're learning here today with sampling distributions is going to go back to things that when we talked about random variables. You guys remember we talked about random variables? Random variables. And do you know what a random variable is? Ooh, that's a tough question. What is a random variable? All right, maybe I'll just answer my own question. I'm impatient here. Random variable, right, is a quantitative variable, right, whose outcomes or whose values are determined by a chance process, right? And so actually when we were when in chapter 7, when we were learning about sampling distributions, we actually learned, whether we realize it or not, we learned that the statistics we calculate are random variables, right? We learned that a sample mean is a random variable, right? Or it's we found that this random variable, right? Why? Because remember how we talk about the randomness condition when we make sample means and stuff like that, and we talk about randomness and independence. The reason that we talk about those things in independence, anyway, that says independence. The reason that we assume these things about X bar is because that way we can treat it as a random variable. We can treat it as a quantitative variable whose values are determined by some type of chance process. So the chance process is which individuals from a population were used to calculate the sample mean, and it's a matter of probability now what we get for a particular X bar. So back in the beginnings of random variables, remember we set up all those tables, right? All the possible values of something, and then we had the probabilities underneath it. We calculated the mean and the standard deviation and stuff like that. And then we would remember how we did a bunch of problems where we said assume that sort of X and Y are independent. And then maybe we'll say like X is approximately normal with the mean of 10 and a standard deviation of 3. Y is approximately normal with a mean of 12 and a standard deviation of 4. And then I'd say something like, ooh, let's describe what's the probability? What's the probability that Y is greater than X? Right? And we would do problems like that. You guys remember when we did problems like that? In order to figure that out, we'd have to figure out we could convert this to something that's like the probability of Y minus X is greater than 0. You guys remember stuff like that? This is actually right now, this was chapter 7. What I'm doing right here is actually chapter 6, right? And we would do some problems like this. The only way to answer this probability question is we had to say, okay, well, what's the distribution of Y minus X? Well, that would be approximately normal. And its mean would be the difference of the means of these guys. So Y minus X, that'd be 12 minus 10. That would mean that we have a mean here of positive 2. So say the mean of Y minus X equals positive 2. And then the standard deviation of Y minus X, remember to do that, did we subtract the standard deviations? Would I do 4 minus 3? Is that how you find the standard deviation of Y minus X? 4 minus 3, is that what it would be? Do you guys remember? What would be the standard deviation of this particular scenario here? Yes, Dominic, giddy the heck up. You would add the variances, and yes, the standard deviation would come out to the number 5, right? Why does it come out to 5? Well, as Anthony said, you add, and you don't add the standard deviations, you add the variances, right? Perfect. So if we said, what was the standard deviation of Y minus X? That would equal the square root of the standard deviation of Y squared plus the standard deviation of X squared. Remember, you add the variances, sort of like the Pythagorean theorem, right? So you would do the square root of 4 squared plus 3 squared, which ends up being the square root of 25, which is 5. And I picked those numbers on purpose so they came out all pretty alike, right? And boom. So all this is chapter 6 stuff, right? Then beautiful. the way we would calculate stuff there, if I want to know the probability that y minus x is greater than 0, then I could just use this normal distribution with a mean of 2 and a standard deviation of 5, right? Boom, mean of 2, standard deviation of 5. Let me get another color in on this. And so if I sketched a little, what would that distribution look like if I drew it up all the way up here? Here we've got 2, 1, 2, 3, 1, 2, 3. So the standard deviation was 5. This would go up to like 7, add 5 again. What's that? That's like 12, add 5 again, 17. Here, subtract 5, that's like -3, -8, -13, right? And so if I want to know the probability that y minus x is greater than 0, I could say, well, where's 0? 0 would be like right around here, and I would shade everything to the right, right? And I'd get that. And I could go to normal CDF. Let's see here, normal CDF. I could go 0 to infinity, the mean of 2 and a standard deviation of 5, paste and Shazam, and there would be your probability. It's like 65.5%. 65.5%. And so anyway, this is all stuff we did in chapter 6, right? So now we're going to take all that and we're going to apply it to chapter now in chapter 10 into thinking about the difference between two random variables, right? And so, you know, I might, what I would do now is I could say, aha, what if I treated x bar, right, x bar as a random variable, right? But I calculated this x bar from some population right here, and this population has a mean that equals say, I don't know, a number like 100, and has a standard deviation of say like, I don't know, 20. And then there was some other population over here, right? And I'm going to calculate some sample mean from this population, a different sample mean. Let's say this population has a mean of say 110, and it has a standard deviation of like, say, I don't know, 14, right? Now, these two means are collected from two different populations. And so I'm going to adjust the notation a little bit because it's confusing if I have mu used two places. So I could call this like mu1 and sigma, mu1 and sigma 1, and I could call this mu2 and sigma 2, right? I'm going to zoom in just a little bit there. Might be easier to see, right? That's mu1, that's sigma 1, that's mu2, sigma 2. And so this I could call sample mean 1, I could call this sample mean 2. And so what I'm doing here is I have these two sample means that were taken from some random sample from this population, right? I'll call this population number 1, and I'll call this population number 2, right? And so I wonder, well, what's the probability, right? That maybe I could ask, what's the probability that the sample mean I get from population 1 is greater than the sample mean I got from population 2? And if I wonder that, right, then I could say, okay, well, that the probability of the sample mean from I could do the similar math that I did before. I could rewrite this as the probability of x bar 1 minus x bar 2 greater than some number 0, right? And then I could just go ahead and calculate away. I could say, okay, well, this distribution x bar 1 minus x bar 2, well, if these guys are normal, let's just say these were normal too, like these are normal variables. It's easier if they are normal, right? Then I could be like, okay, that's totally cool. What am I lacking here? Well, if I want to know the probability of x bar 1 is greater than x bar 2, and these are all I know about this, I also need to know the sample size. So how big of a sample should I pick? Let's say I just pick the sample of size, I don't know, let's keep it small. Let's just say sample size of 9. And this one, it actually doesn't matter if it's the same sample size, but let me call this a sample size of say like 16, just to show that it doesn't actually matter, right? Now, in this case, since I have small sample sizes, it would help. It's important that the populations themselves are going to be normally distributed. However, how big of a sample size could I have picked for it not to matter what the shape of the population is? I'm going to ask you guys, see if can anyone guess how big of a sample size could I have had? And if that sample size was that big, I wouldn't have had to worry about these two populations being normal themselves. Anyone want to say, anyone want to chime in? I'm killing time here. No one wants to chime in. The answer was, the answer is if the sample sizes were at least 30. If they were 30, then it wouldn't have mattered what the population shape was, because that would have made the sampling distribution of the sample mean 1 approximately normal and the sampling distribution of sample mean 2 approximately normal. But since I just said that the populations themselves were normal, it doesn't matter. So if I want to know this distribution here, well, it's going to be normal. Why is it going to be normal? Well, because if you take a normal variable and you subtract from it another normal variable, the result is normal. That's something we learned in chapter 6. So that's great. We've got this. And now what would be the mean of this distribution? The mean would be the difference between these two means. And so I said sample mean 1 minus sample mean 2. So logically, I could say population mean 1 minus population mean 2. So that's 100 minus 10. 100 minus 10 is a negative 10. So that's cool. And then now the standard deviation of this guy, well, I'd have to know about the standard deviation of these sampling distributions. So if you recall, what should be the standard deviation of sample mean 1? Well, the standard deviation of sample mean 1 should be the population standard deviation from population 1 divided by the square root of the proper sample size, which in this case is whatever n1 is, right? So this is n1, this is n2. And so this is just going to end up being what? 20 divided by the square root of 9, right? So that'd be like 20/3, right? And then if I think about it too, then I could say, what's the standard deviation of sample means 2's distribution? That would be population standard deviation 2 divided by the square root of the second sample size. So that would have been what? 14 over the square root of 16. Right. And so that would be like 14 over 4. Right. And so then when I go here and I say, what would be the standard deviation I use here? Remember, you add the variances. So if I said, okay, I would say I've got the standard deviation of x bar 1 minus x bar 2 is going to be equal to the square root of this guy, standard deviation squared of x bar 1, right? Plus the standard deviation of x bar 2 squared. And so that's going to end up being what? 20 square root of, let's see, that guy, 20/3 squared, plus 14/4 squared. And so if I got a calculator out, can you guys see that? 14. Notice I didn't reduce the fraction. Doesn't matter. Don't judge me. All right. And so because I'm just going to be doing a bunch of stuff here. So I got 20/3 squared, right? Plus I'll add to that 14 divided by 4, close parentheses squared, right? And so I've got that. Let me turn that into a fraction just so it's nicer to look at. Oh, what a crazy fraction. 2041 over 36. And so if I take the square root of that, answer, right? Which is some irrational number over 6. If I try to, that's because the square root of 36 is 6, but I can just write that down. That's going to be approximately 7.5296. Anyway, so that's what I could put here as well. So this standard deviation would be 7.5296. Color scheme, getting the red. Okay, and so if I want to know the probability that this sample mean, right, is greater than that sample mean, then all I would do is use this distribution right here. I've got, it's centered at -10, and this is a standard deviation of 7.5. So it actually have to get to 0, I'd have to go even more than one standard deviation above the mean, something like that. So this answer is going to be less than 16%. I could go on my calculator here. I could hit second vars normal CDF and be like 0 to infinity, a mean of -10, a standard deviation of 7.5296 or so. Hit paste, and enter, and I got about 9.2%. So this guy right here is about 9.2%. And so the probability of me just by chance getting a sample mean from this first population of size 9, right? That's bigger than the sample mean I get from this population of size 16. The probability of that happening by chance is 9.2%, right? And so it's going to end up, in terms of the context of what we're learning in this chapter, right, is that this sort of math that we learned to do that combines things from chapter 6, when we were just learning about the difference between two independent random variables, we're now applying, and we're going to end up taking this math for the sampling distributions. And later on this, starting tomorrow, we're going to learn to do a confidence intervals and significance test that's all based on this exact same math. So anyway, that's what we're doing this week. Any questions? I mean, I really gave you a quick mini lesson. In fact, I'm going to, I normally just sort of post these for people's enrichment, but I think I'm going to take this portion of the video and actually make it part of the assignment. So you guys were already here. Good for you. Because I went into a little bit more detail here and actually want everyone to see this. So I'm going to probably cut up this video and take this portion and make it another video for people to watch, albeit at a lower resolution. Any questions from you guys here about any of this stuff that I just showed you real fast? Because again, this is going to be the math that's the basis for when we look at the difference between two proportions and the difference between two means with confidence intervals and significance tests this week. So any questions from you guys?